we'll get started here. So if you're seeing my screen, you see what is the defining characteristic of an independent measures study? And is this what you meant by definitions, things that your instructor would?
Yeah, kind of.
Okay. So, I mean,
just,
like your instructor provides.
I don't even know what it is, so I guess we should go over it.
Yeah, here's the definition from the text here. An independent measures design is a research design that uses separate groups of participants for each treatment condition or population of a group. So let's say I want to do something with bicycles. Maybe a group is men. Maybe a group is women. And these are the separate groups. Okay.
Okay.
Like that's one example. I mean, there's literally infinite examples. Sometimes it's usually to compare this like in context of other things, but the main thing is that there's two groups.
Okay.
And it could be but here's what it's not. It's not before, after. Not at least not for this one. So that's it's not like men, before treatment, after treatment, or women, before pregnancy, after pregnancy, or something like that. It's just they line them up within groups.
Okay.
All right, so question two. So question two, we'll have to get the formula out for this. It says explain what is measured by the estimated standard error in the denominator of the t statistic. So we need the t statistic, and this one's kind of a monster thing here. So they're asking about just this part down here at the bottom, and so we need that formula, and I'm going to snip that in here as well so that you can see it. So S M, this right here is this, and what it is, it's like a weighted standard deviation, because it takes into account both, like this is for group one and this is for group two, and it takes into account the sizes of the groups as well. Now, like what you really care about is what's happening here in maybe question three. This seems more like a potential test question because it's got some numbers in it. So they want you to compute the pooled variance in part A. So part A, this formula right here that we just looked at, that I'm circling here, that's actually the standard deviation. So the variance, the S squared, is S1 or SP1 squared over N1 plus SP2 squared over N2. And they give you those quantities there.
Okay.
So do you want us to do that calculation right now? Or do you want to do it? I guess do you want to do it on your own, or here? They're giving you the numbers. They're telling you that.
Okay, I can try to do it on my own here.
Sure. The thing that instructor didn't do a real good job of is like saying this is N1, this is SS1, this is N2, this is SS2. But
okay. Am I squaring those SS's? Like, am I squaring them?
Oh, I'm sorry. So these are already squared.
Okay.
So when it says SS, that means sum of squares.
Okay.
And you already have it there. So you do not have to square. Good thing to ask, because it would change the answer significantly.
Okay, so it would just be like 25 plus. Oh, sorry. 1 sec. Is it 42.5?
Sounds reasonable. I didn't actually do it. I'll do it right now. Yeah, 42.5. Okay. And then the standard error for the mean difference. is just the let me just check this one more time here. Your instructor's got a lot of formulas going on here. I'm sorry, I gave you the wrong formula here. So let me back off this. Didn't realize your instructor gave you this. Okay. So I'm sorry, the pooled variance
okay.
is actually this formula right here. And it'll make more sense because the instructor gives you the sum of squares. So you actually add the two sum of squares, 100 plus 140. The df1 is n1 minus 1, and df2 is n2 minus 1. Sometimes the formula is written as like n1 plus n2 minus 2, but it's basically you take this first n, subtract 1, plus the second n, subtract 1, and this will give you your final answer.
24.
Yeah, that sounds right. So 24. Okay. So
Okay.
now to do part B, we do need that formula we just looked at. So this value you just calculated right here, this is the s squared p. Okay. So the s squared p is the same in both, and it's already squared, so you don't have to square it.
Okay.
But then you got to figure out what n1 and n2 are, and that comes from here and here. So that's 4, and that's 8. And you do need a square root of that.
Okay.
So that's like 6 plus 3. Wow, this actually worked out really nice. Looks like it's just 3.
Is it plus or minus 3, or is it just 3?
It's just 3 because it's there's no plus or minus out front. You're adding inside here.
Okay.
Now 4 is very much like 3. You can do that here. It's the same A and B. This might be good here to do. So I'll grab the formula again for A. Pooled variance formula. But go ahead and give that one. Wait, I apologize. This one is not quite the same. Variance of, okay. So they're just using they're using variance instead of sum of squares here. Why would your instructor do that?
Am I supposed to find sum of squares?
No, there's an alternate formula here. That's why your instructor is giving you that one. So there's actually two formulas for it. I had to look a little closer in their document here. So this is not used very often, but the formula is you first find the degrees of freedom and multiply by this S1, degrees of freedom, and then multiply by S2, and then you divide here. So in your problem, your degrees of freedom for the first one is 9 minus 1. That's the degrees of freedom. Your S squared is 35. It's already squared, so you don't have to square it. Plus, degrees of freedom for the next one is 3 minus 1. And your S2 squared is 40. It's already squared. All over, and these are added together. So it's the 9 minus 1 plus the 3 minus 1, like that.
Okay. Is it 47?
Sure. Let's just go with that. The numbers
Okay.
aren't super. It's not super. It's more important than the formula. So the standard error, though, the standard error is this formula here, which is the same in both cases. And you have that SP squared number. That's the 47 you just told me. So it's the 47 over N1. N1 is the number of samples, which is 9. It's not -1, so we're 9 plus 47 over 3 square rooted.
Okay.
Do you get a reference sheet or like 1-page piece of paper? Or
Yeah, we do. I have a pretty big, like, she gave us one for the other 2 exams, and I have a pretty big spot open, so I think I'll just fill in with the stuff that the later chapters.
okay, I would, definitely want to have like some sort of reference that, okay, if it's SS, I use this formula. If it's S squared, I use this formula.
Okay.
And then this one is the same for both. And have the words next to it, like this is the pooled variance. This is the estimated, standard deviation, standard error, sorry, standard error. That one.
Okay. Okay, we can.
Okay, so let's go to number 5 here. One of the things that I think would be really common to ask on an exam is like they give you a question, they ask for the degrees of freedom. And like in short, if it's a t-test, it's n-1, but now you're doing a 2t test. Okay, and that's what it's asking for here. So it's n1 plus n2 minus 2. And how did I know that? It comes from the formula here for this pool
Okay.
variance. Okay, because the degrees of freedom down here in the bottom, it's really n1 plus n2, but then you subtract 2 from each of them. So
Okay.
that is that's one measure of it. There's also some formulas whether the data is biased or not. It doesn't look like it's been covered. So anyway, in short, it is 8 plus 12 minus 2, which is 18.
Okay.
But you may be asked for like that. There's degrees of freedom and all the tests that you're doing. So it's something that could come up again.
All right.
Right. That kind of takes care of this. I mean, there's kind of some other questions we could look at, which I think the only one I'll throw in here is this effect size.
Oh yeah, effect size.
So we'll throw in, it's like another formula, I mean, it'll say like, what is the effect size? So I have to give you some numbers here to do this. So let me just go back and grab a question. So when you did this one earlier, these numbers, okay, like it told you, like from this, you found out that S2P, or I'm sorry, S squared P was, let me go back and grab it, because you did this calculation, it was 24. Okay, so you found out that it was 24 from a previous problem. So let's say I tell you that mean 1 is 16 and mean 2 is 12. I have to tell you this, by the way, you can't just do it on your own. You would do a 16 minus 12 over the square root of 24. And you get some number for that.
Okay.
Sometimes the instructors, like, they have like charts for this. It's like if D is from like 0 to 0.2, it's small. Do you remember
Yeah,
any of
she
that?
gave us that.
Okay. Yeah, I don't know. Whatever these are, you have to know what they are.
Okay.
It kind of depends on the instructor in the book, etc. Anything else on that, or can we move to that next chapter?
Yeah, we can move to the next chapter.
Great. Is this going the way you want for the review?
Yes.
Okay.
I'm honestly thinking that maybe we just skip to chapter 14
Okay. Let's go to
because
14.
that's our newest lesson and that's the stuff I haven't really seen.
Sure. All right. Okay. All right. So let's let me snip in a question here. It's kind of a question, but so you're on
Yeah,
regression.
sorry, these docs are weird.
Yeah, it's okay. So at least you got something here for us to work on. And so the instructor here is like, normally you would just start out with a table of X and Y values.
Yeah.
And you might have to calculate everything else. Okay, so let me just try to explain how some of these values are. So MX is the mean of X and MY is the mean of Y. Okay, and you can see they just add up the values. These are the sums. They add up the X's, divide by the number of X's. Same thing here to get this. So this X minus MX is 4 minus 3, 2 minus 3, and so on. Okay, to get that value. So it could be positive or negative. Y is the same deal. It's 13 minus 9 to get 4, 5 minus 9 to get minus 4, and so on. And then like really X minus MX goes to this column because then you square the value immediately. So it becomes, these become positive. Same thing here. So if you had to do this on your own, you actually could go right to these two columns. Like you don't actually, like, these are intermediate values that you don't care about, X minus MX and Y minus MY. It's the squared values. And then again, they add them up here again. This is the sums. So they add these up to get 10, add these up to get 50.
Okay.
And so actually take back what I guess they use them again in here. X minus MX times Y minus MY. So she's showing the formulas here. But again, what you really care about is the sum.
Okay.
So you you can, I don't know if you'll expect this, you can take a little set of data like this, produce all these values, and then the thing that you're going to be asked to find is R. R is the following. It's this SP. Okay. SP in this case is the is this number right here. So this is see how it's the sum of products, that's SP. So it's 20 over the square root of sum of squares X, and your instructor showing that here 10. So the sum of this column times sum of squares Y 50. Okay. And you get a number, you get like 0.889 when you do that.
Okay, yeah, I got that.
Okay, so then it's possible for this number to be negative up top here. Okay, but if we were to make a quick plot of this data, the XY pairs here, 4, 13, 2, 5, 5, 12, 1, 6. Do you agree that a trend line, a line that goes through the data, kind of goes up and to the right?
Yeah.
So that has positive slope and it has a positive correlation.
Okay.
Okay, so let's talk about what values R can take on. R can be everything from -1 to 1.
Okay.
Okay, and when now we have to talk about the absolute value of R. So the absolute value of R tells you the strength, and this is a question they'll ask, the strength of the relationship.
Yeah, that was asked on the last exam, so I'm sure it will be.
Yes. So if absolute value of R is closer to 1, and again, it's kind of ranges. It's like, I don't know, like 0.8 to 1. This means it's strong. And again, we're talking about the absolute value of R. So a question you might see on an exam would be something like, which of the following, let me actually write this down. Which of the following is the strongest correlation? And the answers will be like A, negative 0.9, 0.1, negative 0.4, and 0.85. And you're supposed to know that you actually look at the absolute value of these numbers. This is really 0.9, this is really 0.1, this is really 0.4, and this is really 0.85. And which is the biggest? That one.
Okay.
So it doesn't matter that it's negative. It matters that it's closest to 1 when you take the absolute value of it.
Okay. So no matter what, look at the like the absolute value of the number.
Yes, because this is the standard test question they ask in this stuff.
Okay.
Okay, so the correlation is the same sign as the slope. So like if they tell you the correlation is negative 0.4, that means it has a negative slope.
Okay.
If they tell you the slope is 5.9, that means it has positive correlation, because they have to go in the same direction. If the correlation is positive, slope is positive. If correlation is negative, slope is negative, and switch them around.
Okay.
And that is somewhat shown here in this picture. I guess this kind of summarizes it to some degree. You know, positive slope, positive correlation, negative slope, negative correlation.
Okay.
The graph that is missing is no correlation.
Yeah, that's just a bunch of dots, right? Like
Yeah,
no.
and then sometimes they're like, well, what do you use as your estimate? You use y bar, which is the average of the y's,
Okay.
as your estimate. Hey, I just need to jump off here for 30 seconds. I'll be right back.
Okay, no worries.
Back.
Okay.
So so then the another type of question you might see, which is something like which of the following values of R is impossible? And so it could be something like A is 0.5, that's fine. -1, that's fine. 1.2, that's not okay. And then whatever else, you know, 0, value of 0. It's because R, again, R has to go from -1 to 1.
Okay, so why would -1? Why would B not be?
Because these include the endpoints.
Okay. Okay. So like -1.0 does not count.
Yes. Yes.
Okay. Wait, so why not 0?
0 is between -1 and 1. It's right in the middle.
Oh, you mean, okay.
Yeah, this is interval notation. Sorry for not being clear on that. That means that everything from the left bound to the right bound is okay.
Okay, so
Like on a
C
number
would
line.
be the answer?
Yeah. Yes. Because it's
Okay.
greater than 1. It's
Right.
greater than
And
1.
all those answers are possible, all the other ones.
Right.
Okay.
Right. And so, I mean, not to be confused with slope. The slope can be anything. The
Okay.
slope of the regression line, I mean, it can be 5,000 up or negative 1 million down, but the R value is always between 0 and 1. Or I'm sorry, -1 and 1.
Okay. Sounds good. We can move to the
Okay.
next.
One other question here. Oh, this is really important. I hate saying stuff like that, but because I know it'll come up on an exam, and you probably saw this. Correlation does not imply causation. And what that means is like you can correlate two things that don't seem to be at all related, like the number of PhD students at ASU and the number of cow births last year. And they're not related at all, but you can get a correlation. So it doesn't mean that one causes the other.
Okay.
So keep that in mind. All right. So that's all there is to say about that. That's chapter 14, which is the next one to look at here.
I guess we could just go back 11 to 11 and then 12
Okay,
if we have time for that.
let's do it. Okay. Chapter 11 is what's called a repeated measures. So chapter 11 is called repeated measures. I prefer the term paired. So it's like you take one group, not only that, one group, and there's generally like a before and an after measurement. Now the small variation on that is like sometimes it's like left hand and then you use something with your right hand. Okay, but this is like you're testing out a new drug and you give it to the group, but before you give it to them, you like measure their weight before and then your weight after. It's the same people. You know, if this person was,
Right.
150 and the drug worked, it's 145 maybe. Okay, or like you did something, but just to that group. So yeah, so your instructor here, this is a weird table, but let me snip it in anyway, try to explain it. So weird. So like your instructor keeps using the word treatment, which is probably correct, but like I would look at this as like before and then after. This is like Matthew here, and he did something and he got a score of 5, and then you did something, so some amount of time passed, or you did something here, and now I got an 8.
Okay.
And then B is like you got 6, and then you went up to 13, and C is your friend, and D is your other friend. Okay, this D bar, this is after minus before. So really it's 8 minus 5 equals that, 13 minus 6, 10 minus 7, 12 minus 9.
Okay.
So why do you need that? Because the formula for the test statistic, although it doesn't seem like they want you to find that, is okay. So the first thing you find is MD, and that's the average of these. So it's the 3 plus the 7 plus the 3 plus the 3 all over 4, and you get some number for that, which actually is 4.
All right.
Okay. So your instructor gives you a problem here. So we should probably do it with this problem here. The truth is that after you get the differences, you don't need anything else in the problem set. But let me try to show you that. So like your instructor gave you the differences, 5 minus 3, 4 minus 2, like this is all you care about now. This is like your data that you actually are interested in. And you probably remember back early on in this course, you did like X minus X bar squared. Do you remember doing that? Like taking, getting the average of these, and then, so you actually do exactly the same thing as you did there.
I think it might have been like she called it something else though. Is it like a different formula?
Well, this is just finding the standard deviation, like, but that's what's next. So the question here is to find the first thing it asks for in this problem. Let me snip this in. We need to find MD, which is adding these up. 2 plus 2 plus 4 minus 1 plus 3 over 5. Okay, so that is what, 8, 7, 10, or 5. This is 2. Okay, so now for each of these, we have to take this data point, subtract the mean, 2 minus 2, and then square it. So that's 0. 2 minus 2 squared is 0. 4 minus 2 squared is 4. And then minus 1 minus 2 squared is 9. And then 3 minus 2 squared is 1. If you add these up, you get 14. So your instructor actually provides that number here, although you can certainly find it. They provide it in the problem here. Because the next thing they ask for is s squared. S squared is this SS number divided by n minus 1. So that's the same standard deviation formula.
Okay, yeah.
So it's
So that's
14.
the one I recognized.
Yeah, over 5 minus 1. So it's 14 over 4, it's 3.5.
Okay, and then just going back here, when you're doing those calculations on the right, like the 2 minus 2 squared,
Mhm.
you're taking the MD and then that's the 2.
That's
It's
right.
consistent. But
That's
then
right.
what number is 2, 2, 4, negative 1?
These right
Oh,
here.
that's that D.
That's why I said these
Okay.
don't matter anymore. Like once you get this, you only care about,
Okay.
you treat that as your data. That's like going back to
Okay.
chapter 2 or something in this class. And
Okay.
okay, so your SMD is the square root of 3.5.
Okay.
It's whatever that is.
The problem with this class is there's just so many formulas. Like
Yeah, it's an
it's
entire
pretty simple math. It's just like a lot to memorize almost.
Okay, so now we actually get to the stuff that like beyond just those calculations. This is the questions here. So state the hypothesis in words and symbols. So the hypothesis is always on, let's see if you actually have it up here. So you don't, but it's always on it's mu d, the mu d. So the mean difference between these two groups. Okay, I can't remember if your class always uses one tail or two tail. In this class, let me see what you guys have. Change. Okay, so if you go back, see what it says change.
Yeah.
Change means usually it means equal to 0, then not equal to 0. So we're going to go with that it equals 0, and then change, because it doesn't say whether it changes positive or negative. Although I guess you could imply that it's they want to know whether positive attitudes, like it's almost like it's almost contradictory. Like positive means that it would get bigger. Do you happen to know if there's a solution to this to check?
Let me look back on my chapter 11 notes because I know our hypothesis stuff kind of changes each chapter. I don't see anything in my notes, but 1 second. It wouldn't be like, it would be equals or doesn't equal to 0, right? It wouldn't be like less than.
Well, so see that. Okay, so like the way I would write this is a psychologist wants to know whether a new program has increased attitudes, because when I look at this data, like it looks like it's increased the attitudes.
Right.
So that would change the answer down here to, because the null always has to have an equal sign in it, to this. I'm sorry. to this means that they either did not change or they got worse, to the thing we're trying to prove. This is what we want to prove.
Yeah,
that
so
they
that's
got,
what I have in my notes, what you just wrote
yeah,
down.
exactly. But the way it's written, it could be equal 0, and then change just means either it went up or down.
Okay.
So I mean, I don't think this is right, but it, this is the gray area of this class that, really is instructor specific, and the questions have to be worded. All right, so the next thing is to determine the critical region for this.
Okay.
So let me snip that in. So the critical region here, you always, you hopefully you've been doing this, you draw this bell curve, okay? Because it's right tail, that means when it's greater than 0, that means it's right tail. That means this alpha value is all over here. This region right here is the area here. The area is 0.05. And they want this critical value. They want this t value. So to do this, you either use your calculator or you use a table, but you're doing an inverse, an inverse t lookup. And you need to know the degrees of freedom. Any of this sound familiar?
Yeah.
Okay,
sure.
that's good. That's good. So the degrees of freedom is simply the number of samples minus 1. So you have 5 participants. So your degrees of freedom here is 5 minus 1. So you're looking at a t table, or using your calculator, whatever you like, and you're coming up with that number. I think we were doing this once before. Sorry, I gotta pull up my calculator now.
I have a T table printed out here. So I'm looking at 0.05 and degrees of freedom 4, right?
You're looking at 0.05 degrees of freedom. So let me get QT 0.04. Yeah, so I get 2.132.
Okay, yeah.
Is that okay? I mean, is that clear?
Yeah, wait, so I know like degrees of freedom is n minus 1, but where'd you get the 5?
Because that's n. Your n is 5 samples.
Is that in the problem?
It kind of is. You have to interpret it. See, there's 5 participants.
Okay. Okay, yeah, we can move on.
Okay, so the reason you need the critical value is you actually are going to use it with the test statistic. If this were me, I would actually calculate test statistic first. The test statistic is going to be compared to that value. So the test statistic here is, I mean, it's not all that complicated. So you already know this mu d. This mu d almost always equals 0 in most of the problems you're doing. MD is the mean difference between them. So if you go back up and look, your mean difference was 2. And then your SMD, the standard error, is the number you actually calculated already up here. You calculate over the square root of 3.5 as your SMD.
Okay.
So you get this number, and then you compare it.
Okay, so I got 1.06.
What did you get for that?
1.06.
Okay, so like if we draw another thing here, okay, here's 0, here's your number 1.06, here's the 2.132. So you reject here you fail to reject.
Okay.
You're going to fail to reject.
Okay. Got it.
So that's step 4, make a decision about it. Okay, so the next thing here, this is such a small, like, it's such a small little wrinkle to this like thing. Like, I mean, you could be, I mean, it's reasonable to ask this, but you have to, you have to know what you're looking for. So Cohen's D here is MD, which you already found is the 3 over the S. It's actually the same value you just found. The square root of 2.5, it's the 1.06. So they could ask that for sure. The next thing that they show here is a confidence intervals. Did you have much of that emphasized in class?
Kind of, yeah, we learned it. I'm not very good at it. I don't really like know very well, honestly.
Okay. So they have to tell you the confidence interval. So your instructor has to tell you, like, I want a 95%. They have to tell you this, because this number leads you to the t value.
Okay.
So right now, like this is the formula right here. It's really not that bad. You actually already have this for the problem. You just did, it's 3 plus or minus, okay, the t value, which we're gonna get from the table. So we're gonna get that number. And then we multiply by SMD, that was the square root of 2.5. So see how you already have this? You already have most of this. The MD is the mean.
Yeah.
SMD you already calculated. Okay, this T, how do you get the T? Well, 95% confidence interval means that there's half in each tail, 0.025 in this tail, 0.025 in this tail. So it's another one of those inverse T lookups.
Okay.
But you need your degrees of freedom. Your degrees of freedom in our problem was 5 minus 1 equals 4. But now you're looking for 0.025 in the tail. So let me give you that number, and you can see if you can see how I got that, or look on your chart or whatever you're using and see if it's
2.776.
yes.
So what alpha am I looking at?
Well, again, it's like, because it's 95%, that means there's 0.95 in the middle, and then there's 0.025 on each side. Like it's there's lots of ways. It's like 1 minus alpha divided by 2. Well, sure, if you want, but it's also either or way of doing it. But if you choose the wrong number, you will get the wrong confidence interval. So you gotta be like, okay, like, how much is in the tail? It's the same in each tail. So then once you get that number, it's really 2 calculations. It's 3 plus 2.776 times the square root of 2.5. And it's 3 minus 2.776 times the square root of 2.5.
Okay. Okay, I see how that works.
Okay, so then the last thing that's related to this that generally comes up is they ask a question like which of the following is the correct interpretation? And there's all these answers, but the one you want is, we are blank percent confident. So these I think you can see it, these fish things, or what, I don't know what you call them. They're for insertion. Confident that the true mean, and then and this is where you're going to insert the context of the problem, is between lower value and upper value. So it's always in this form. And so, like, you'll see this, but it'll say, like, like, it'll just be in the wrong, it'll be the wrong like order. It'll say, between lower value and upper value, we are 95% confident, but it's got to be exactly this language in this order
Okay.
when you see it.
All right. Sounds good.
All right, so there's a couple of more confidence interval examples on this page that would be good for you to maybe look at. We weren't able to get through chapter 12, or I don't remember the next one. Do you have some more time before your final to study for this, or is it like tomorrow?
No, it's on Tuesday, and I think I have another appointment with
Oh, excellent. Great.
tomorrow.
Okay.
Yeah, we can finish that up.
I'd recommend, doing as much as you can to review what we did today, and then, we'll just pick up next time where we left off.
Okay, perfect. Thank you so much.
You're welcome. Thanks so much. Talk to you later. Bye
Have a
now.
good day. Bye.